This is the Unit 11 review, which comes from Chapter 11, which covers areas. On our first problem, we're looking at finding the area of our figure. Now, we don't have a specific polygon name or area form that we could call that. We're going to break it up into pieces, and we can always break something apart, find the area of the pieces, and add them together. We're going to see that on quite a few of these problems today. So if I cut it here, it gives me two rectangles. The first rectangle is 8 as a height, and it would be 8, 8, and 8, or 24 as a base. And then it has the bottom rectangle, we could even number these if we needed to, is 8 by 10. So when I look to find the area of each of these, for the first one it's going to be 8 times 24, which is 192. The second one is 8 times 10, or 80. I then have to find the total area by combining those two. 192 plus 80 gives me 272. And that's units squared for our answer. Next problem, we could cut it this way, or we could just cut off this last piece here, but we have to find the correct dimensions. We have to be careful here. So the big rectangle, call that 1 and this one 2. The big rectangle has 9 as a base and 8 as a height. And then for the small rectangle, we have 7 to here, and this is 9, so that actually leaves 2 left over for its base. And 11 is the total height, and we go up 8 for the first one. That leaves 3 for the other. So the area of the first one is 8 times 9, which gives us 72. Area of the second one is 3 times 2, which is 6. 72 plus 6 gives us 78 units squared. For number 3, we need to find the area of the trapezoid. Our formula for the trapezoid is 1/2 the height times base 1 plus base 2. So 1/2, when we pick the height, we have to make sure it's perpendicular to the bases. The 2 is perpendicular to the bases, the 4 is not. So it is 2 is our height, base 1 is 6, base 2 is 8. I'm going to simplify here. If I notice 1/2 and 2, I can cross those out because those are just 1. That leaves me with 6 plus 8, which is just 14. Number 3, we're trying to find the area of the shaded region. Now this is really two parts. We have the square, and we're subtracting the circle. So the square would be the whole thing, but we want the part that's not the circle. So in this case, we can actually literally subtract the areas away. Our square is 8 by 8. Our circle, on the other hand, though, is going to have a radius, because that's really what we want when we look at a circle. We want the radius for the area. Since it's 4 all the way across, that would be its diameter. Its radius is 4. I'm sorry, it was 8 all the way across, so its radius is 4. So to find the area of the square, it is 8 squared, or 64. To find the area of the circle, that's pi r squared, so that's pi times 4 squared, which is 16 pi. Now, they're not like terms. I can't subtract them, but if I just write it out, 64 minus 16 pi, that actually shows it pretty clearly what I did. Area of the square is 64, and I'm subtracting 16 pi, and if I look, it's in terms of pi for my answers, so answer C is what I want. Number 5, we have a regular pentagon with sides at length 6. Another pentagon has side length of 8. We need to find the ratio of the area from the smaller to the larger. So we're going small to large. And we first can write a ratio for the sides, and that was 6 to 8. Anytime we do that, we want to reduce. So looking at ratio of sides, it's 6 to 8. That's not the same as the ratio of the areas. The ratio of the areas is actually this ratio squared. So we have to square it to look at areas, and we get it as 9 over 16. So that is A. For number 6, we have the area of the square is 36 centimeters. So if we have a square where the area is 36, we know the area for a square is side length squared, so 36 equals the side length squared. That tells us the sides are each 6, or 6 times 6 gives us 6 times 6 gives us that area, so that means these are all 6. Then to find the perimeter, 6 plus 6 plus 6 plus 6, or 6 times 4 gives us 24. On number 7, we need to find the length from A to B. So we're looking for this length of the circle. We don't want the entire circumference, we want that portion of it. We have the diameter is 20 inches, and the measure of angle AOC is 120. Now that's a little deceiving because we're not actually going to use the 120, we're going to use the angle next to it. We need to use the angle that works to AB. Since this is the diameter, we know this is 180 degrees, which leaves us 60 here. Now, the way we find this, the length, it's the measure of the angle over 360 times our circumference, which is 2 pi r. Now, they did give us the diameter, so technically you could use the formula for circumference using diameter, which is just pi times diameter, but I like to be consistent and always go 2 pi r. That way I'm making sure I have the radius and I can be careful as we go through it. So the angle we wanted is actually 60. So 60 over 360 times 2 pi times 10, which that becomes 20 pi, and I have 1/6. So I'm taking 1/6 of the entire circle, and the entire circle would be 20 pi around it. That becomes 20 pi over 6, which is 10 pi over 3. We can leave that in terms of pi, just like that. You could represent it as the decimal, but as you notice, the answer is in terms of pi. All the answers there. And we match that up, and it is answer D. For number 8, we need to find the area of the figure. This is a rhombus, so we know these are perpendicular. We have, for a rhombus, it's 1/2 diagonal 1 times diagonal 2. In this case, we actually have to use this triangle in that rhombus to help us, because we know one of the diagonals is 6, and that's this horizontal one. But we take the slice out, this triangle, we have a right triangle there, and we can use that to help us find our other diagonal. By Pythagorean Theorem, we would have here that 5 squared equals 3 squared plus x squared, 25 equals 9 plus x squared, 16 equals x squared, and x ultimately is 4. That tells us that this is 4. In a rhombus, those diagonals bisect each other, so that would also be 4. So now we know our diagonals are 6 and 8. Make sure you add to get the total length of the diagonals. So that's going to be 1/2 of 48, or 24 units squared. And number 9, we need to find the area of the shaded region. So this is like that length problem we had, but this area is going to be the measure of the angle over 360 times the area of the entire circle. We ultimately have this fraction because that's going to tell us what fraction of the entire circle we want. So, right angle there, that tells us 90 over 360 times pi 8 squared. 90 over 360 is 1/4, and then we want 1/4 of 64 pi. 64 pi is the entire circle. We want 1/4 of that, so that is ultimately 16 pi. And that's millimeters squared. Let's not forget the units. For number 10, same idea as number 9. It's going to be the area is equal to the measure of the angle over 360 times pi r squared. We need to make sure we pick the correct shaded region. 220 is all of this. We don't want that. We want 360 minus 220. We want the 140 degrees. So make sure you're clear on that. Find that shaded region. So it's 140 over 360 times pi 9 squared. Well, 140 over 360, I can cross out the zeros. Gives me 14 over 36. I can take half of each of those, and that gives me 7 over 18 times 81 pi. Not as neat of a fraction here, 7 over 18. I mean, 1/4 is more common. We'd all agree for that. But if we want 7/18 of the whole circle, it's the same idea. We will want what fraction of the entire area do we want. We could actually reduce this, 81 and 18. We can each divide them by 9, and that gives us 7 times 9 pi over 2, or 63 pi over 2 units squared. If you didn't see that, you could ultimately just multiply 7 times 81 and then have to reduce anyways, but we should get to 63 pi over 2. Number 11, we have, let's see, our measure from A to B is 16 pi over 3. We need to find the radius. So we go back to, let's slide up here, this problem right here. The reason how this problem differs is we get this value to start with, we get the angle, we have to figure out our radius. So we're just kind of solving it backwards here. So our length is equal to the measure of the angle over 360 times 2 pi r. Get an extra paper here, we're out of space. So our length, we said, is 16 pi over 3. The angle is 80 over 360 times 2 pi r. The nice thing is this is in terms of pi. We don't have a decimal here, so it's going to be a little nicer to clean up. I get 16 pi over 3 equals, well, 80 over 360, we can cross out the zeros. I can divide both of those by 4, and that gives me 2/9 times 2 pi r. This becomes, on the right side, 4 pi over 9 equals r. We're going to basically move this over. The way we're going to move this over, we can multiply by 9 and then divide by 4 pi, or you could multiply by the reciprocal of it. If we just go one at a time, I'm going to multiply by 9, and then I'm going to divide by 4 pi. That gets us to r. I cross out the pi's here. I cross out 9 and 3. I can reduce 16 and 4, and it looks like we get a radius of 12 when all's said and done. So that's answer B. And a lot of that is just getting that set up and then solving with your algebra skills. Okay, next page. Number 12, we're finding the area of our kite. Area of a kite is 1/2 diagonal 1 times diagonal 2. If we look, we know one of the diagonals. We know that vertical diagonal would be 8 plus 28, which is 36. And then we need diagonal 2. Now, in a kite, when it cuts with this vertical line here, this value for this diagonal is actually the same as the one over here. And this is where a kite we can actually fold in half and match those up. So that's going to be 24. So half, we could take half of either values. Let's say we take half of 36. That is 18. So it's 18 times 24, which is 432 units squared. Okay, next problem. Need to find the area of the two shapes here. When I look at these, I see the two shapes that I could use as maybe the rectangle and a triangle. Rectangle first is 21 by 30. So that area is 21 times 30, which is 630. Now for the triangle, if I kind of turn it, I have a 6 here, a 10, and a 17. Well, we already actually know the entire length is 21, so that helps us a little bit. But we need the height because the triangle is 1/2 base times height, and we don't have that yet. But if we notice, the 6 and 10 actually form a little right triangle here, and we can use that to find our height. So that's going to be a right triangle. That's going to lead to Pythagorean Theorem. Let's go space over here. I have 10 squared equals 6 squared plus h squared. When you solve Pythagorean Theorem, this is a Pythagorean triple, so it comes out to be h squared is 64, or h is 8, which gives us 8 there, which gives us 8 in there. So it's going to be 1/2 21 times 8. I could just take half of the 8. It's 21 times 4. which run out a little space here, but it is 84. Last thing I have to do is combine the two. It'd be 630 plus 84, and that gives us 714 inches squared is our area. Okay, number 14, I need to find the area of the well, I have the area of the trapezoid. I need to find the height. My formula for a trapezoid is 1/2 height times base 1 plus base 2. I plug in what I know. 30 equals 1/2 h times 6 plus 9. That becomes 30 equals 1/2. Let's move that 6 plus 9, which is 15, equals h. 15 is an odd number, so taking half of it may be a little... Give me a decimal, it's not impossible, but why don't we take that 1/2 and multiply both sides by 2, which moves it over here. 60 equals 15h, and that eventually gets us to h equals 4 centimeters. Number 15, we need to find the area of our parallelogram. For parallelogram, it's base times height. Now that 14 is not the height. The height would be here. But we have a clue here to help us. It's at 45 degrees, because that actually gives us that 14, 45, and h are a special right triangle. Now, for a special right triangle, if I know the hypotenuse and I want the leg, I have to divide it by root 2. So it'd be 14 over root 2, which I have to simplify. I get 14 root 2 over 2, which is 7 root 2, and that is my height. So now when I say base is 26 times 7 root 2, I would do 26 times 7, which gives me 182 root 2 units squared. Number 16, we need to find the area of a kite. So in this one, we have a side out here. Well, we know this side's the same, but that really doesn't help us. We eventually have to get 1/2 diagonal 1 times diagonal 2. But again, we have clues. We have that 30 degrees. If I take that 30 degrees, let's draw a triangle with it off to the side. That's a 30, 60, 90, another special right triangle. If I take the hypotenuse, the shortest leg is half of that, so that's 9. From the shorter leg to the longer leg, I multiply by root 3, so that's 9 root 3. So I have 9 and 9 root 3. In a kite, we know that when I have this diagonal cutting it in half, I can fold it over. This would also be 9. And now we have that 45-degree angle. That gives us this triangle with a 45, a 9. We need this value. 45, 45, 90 is an isosceles triangle, so this would also be 9. So there's our diagonals. I have 1/2. The vertical one is 18. And the horizontal one is actually 9 plus 9 root 3. So I can simplify. I get 9, that's half of 18, times 9 plus 9 root 3. I then distribute, and I get 81 plus 81 root 3. They want it in simplified radical form, so a little neater. 81 plus 81 root 3. Do I have units? Nope. Units squared. So that would be our most simplified answer. I know it seems a little counterintuitive. Maybe it'd be nicer to have an actual decimal to it, but again, this gives us a clear representation of did you find the correct answer. It's easy to see, are your values correct? Okay, on to the last page, number 17. Let's move up here. Area of our shaded region is 27 pi over 2. We need to find the measure of the angle. So we go back to our formula here, and it's going to be the area is the measure of the angle over 360 times pi r squared. We figure out what we know. We know the area. We know the radius. We're solving for the angle. So let's say 27 pi over 2 equals, let's just call the angle x, just to make it a little nicer value to solve for, times pi times 6 squared. We get 27 pi over 2 equals x over 360 times 36 pi. I can write, let's see what we should do first here. Let's move it up here. 27 pi over 2 equals, let's call it 36 pi over 360 times x. And that's just rearranging it together. Now I can reduce this. 36 over 360 actually becomes 10, or 1 over 10. So now I actually have pi over 10. If I multiply by the reciprocal to the other side, the 10 goes on top, the pi goes on the bottom, and that gets x by itself. Now I can reduce, cross out the pi's. I can take 10 over 2 and make that 5 over 1. So ultimately is 5 times 27 gives us that our angle originally was 135 degrees, which again was the measure of MPN. So put that right there. Okay, 18 through 20 are dealing with our regular polygons. If I have a 14, I can put it here, and I have a little right triangle cut out there, which means half of it is actually 7. And now I need to start working through and finding some things. So first off, the apothem is this height that I have. The radius is this solid line and this triangle. Now, this is a hexagon. Since this is a hexagon, if I was to divide 360 by 6, I would get that each of these angles here, the central angle, would be 60 degrees. I then take half of that and makes each of these 30 degrees. So I really have a 30, 60, 90 here, where that is 7. If that's the case, my longer leg is 7 root 3, and my hypotenuse is 14. So that answers 2 of our 3 parts we needed. The apothem is 7 root 3. The radius is 14. Now I have to find the area. So the area formula we have for regular polygons is 1/2 the apothem times either the perimeter or the number of sides times the side length. We typically know 2 of these when we start off the problem. But I've already really found the stuff I needed, so I should have all this information already. My apothem is 7 root 3. Number of sides, well, it's a hexagon, so it's 6. And my side length was 14. So I could do 1/2 7 root 3 times, well, let's do 6 times 14 first. That's 84. I could then take half of that, and that leaves me with 7 root 3 times 42. And then 7 times 42 gives me 294 root 3 units squared. Okay, next one, 19. Now, in this one, our central angle is 360 divided by 3, so that's this angle would be 120, but I take half of that, so that's 60, so I have a 30, 60, 90, really going the other direction. Now, my side length is 6, that makes half of that, 3. Then to get the apothem, or the shortest leg in that right triangle, I divide 3 by root 3. Simplify that, I get 3 root 3 over 3, which is just the square root of 3. And my radius is twice that, because it's just twice the shorter leg, so that's 2 root 3. Apothem is root 3, radius is 2 root 3. Now, let's find the area. 1/2 the apothem times the number of sides times the side length. 1/2 root 3. Number of sides, it's a triangle, so it's 3. Side length is 6. 1/2 root 3 times 18 gives me 9 root 3 units squared. Okay. Last one here is a square. In a square, we have our central angle. 360 divided by 4 makes this 90, which makes this triangle a 45, 45, 90. If this was 10, this would be 5. In that special right triangle, it's isosceles, so that's also 5. and the hypotenuse would be 5 root 2. Tells us our apothem is 5, radius is 5 root 2. Now you may be noticing here we don't technically need the radius to solve for the area. It just may be something you'll be asked to find. So just be aware of that. The apothem, number of sides, and the side length are the important ones though. So 1/2 the apothem times the number of sides times the side length. Apothem was 5. I have 4 sides, and my side length was 10. So I get 1/2 times 5 times 40, which is 1/2 times 200, which is 100 units squared. Now, take a second, look back. You really could have already found the area because it was a square. We knew each side was 10. We could have just squared them. But we did go through, found the apothem, found the radius. But we didn't technically have to do that if we were just asked to find the area. So kind of could have saved us some time. But 100 units squared is our answer there. Okay, let's clear that away and do our last 2 problems. So we have 2 tangent circles inscribed in a rectangle. The width is 12 and the length is 24. We're going to find the area of the rectangle, and we're going to subtract 2 times the area of the circle. Since they're the same circle, we just need to find the area of one of them and just double it. So our rectangle is 12 by 24. Since 12 is this width, that's its diameter, which means our radiuses are 6. So the area for the rectangle, 12 times 24, gives us 288 centimeters squared. The area for our circle is pi times 6 squared, or 36 pi. So we're going to do rectangle minus 2 times the areas of the circles. Gives me 288 minus 2 times 36 pi, or 288 minus 72 pi, and that is centimeters squared. That is in terms of pi, and that is an acceptable answer for us. Okay, the last one, you need to find the area of the polygon. We have -3, -3 for A, -1, 5 for B, 3, 5 for C, and 1, -3 for D. Now the first thing we have to do is figure out what shape we're looking at. That is key, and that way we pick the correct formula. We look at it first, it does look like a parallelogram. I have opposite sides are parallel. So for a parallelogram, it's base times height. Our base is 1, 2, 3, 4 units. Our height is that perpendicular distance to the base. 1, 2, 3, 4, 5, 6, 7, 8. Could have also found that because from A to D, all the -3's are the same, but -3 to 1 is 4. That's the base. From A to B, we look at it, they go on the x value, or the y value, I should say. -3 to 5 is a change of 8, and that occurs for those. So that is our height. So base times height is 4 times 8 gives us 32 units